So Lagrange multipliers are a technique that's used to find the extreme values of a particular function under a given constraint. I'm going to show this in two different ways, okay? The geometric way and the algebraic way. We're ultimately going to need the algebraic way to do what we're going to do. But the geometric way is pretty, and I would feel bad if I didn't show it. Okay? So, let's suppose we wanted to find the maximum value of x cubed y on the ellipse two x squared plus 5y squared is equal to 10. All right? So the geometric way goes like this. We're going to graph our constraint. Clearly, y can't get as large as x can. So the ellipse is going to look like this. All right? Now what we're going to do is we're going to graph some level curves of the function that we would like to extremize. X cubed y. So they'll look like this. All right? Whereas I go away from the axes, the value of the constant gets bigger. Okay? Now, we can just look at this and ask, does this curve represent the maximum value of f of x and y on the ellipse? I mean, it certainly intersects with the ellipse. F of x and y can take, and does take, the value associated with this level curve on the ellipse. But you see how it's obviously not the maximum? Because, I mean, I could just go right next to it and get a bigger one. Right? The problem is that this goes through the constraint curve. I have values on either side of it. Same thing with this one. I could get bigger or smaller. All right, while staying on the ellipse. Clearly, this one doesn't work. It's too big. So, if you think about that, you should be able to convince yourselves that the maximum value occurs on a level curve that is tangent to the constraint equation at the point where it intersects, so that it only intersects at one point. Now, if you remember from multivariable calculus, the thing that characterizes the tangent lines to level curves is the gradient. So we need the gradient of these two functions to be parallel. All right? So if my constraint equation was written as g of x and y equals 10, and my function to extremize is written as f of x and y, then we would say gradient f is a multiple of gradient g. This lambda is the Lagrange multiplier. Okay? If I wanted to solve the problem, we just solve it right now. Fx equals lambda gx. Fy equals lambda gy. At this point, I want to cancel out the value of lambda. If I'm only interested in the value on the ellipse, then I don't care what the value of lambda is. All right, lambda is only there as a surrogate for the constraint equation. It's there to enforce the constraint equation. All right, since we've said we need to satisfy this, we're just looking for the maximum value. The value of lambda is unimportant for us. Okay? So what I'm going to do is I'm going to multiply the top equation by 5y. I'm going to multiply the bottom equation by 2x. And then I'm going to subtract. All right? Now, clearly we could take a factor of x squared out of the left-hand side. So x could be 0. But I got news for you. X equals 0 is not going to give us the maximum value of x cubed y on this ellipse. So yes, while it's true that I would lose points if I didn't point out that solution in Math 3, okay, x equals 0 is not the solution you're looking for. Okay? So we're going to have 15y squared equals 2x squared. And now, of course, we'll plug that into the constraint equation. 2x squared equals 15y squared. 15y squared plus 5y squared equals 20y squared. So y is going to be plus or minus the square root of a half. Okay? So that would give us the value of y. X is going to be plus or minus the square root of 15 divided by 2. Okay? And so the maximum value, we could write it out. All right? I would have 15 root 15 divided by 8 root 2. All right? You can write in your competition math, blah, blah way if you want to. All right? Now, this will also find the minimum value by the same argument. Okay? It's really a nice argument. It's a nice way to see why it is that the gradients have to be parallel. All right? We can also, just before I go on to this other thing, we should notice that just because we didn't care about lambda in this problem doesn't mean that lambda isn't important. All right, so let's say that I was a company and my constraint equation had to do with how much money I was donating to my favorite charity through my business each year. Okay, now maybe I want that. That's a constraint. I do want to satisfy it. But maybe if I found out that donating $100 less to that charity would allow me to triple my profits, all right, maybe I might consider doing that. Okay, that's where the value of lambda is important. If lambda is large, that means that it's hard to satisfy the constraint. If you were to relax the constraint a little bit, it would give you a significantly bigger maximum. That's lambda is large. Lambda is small indicates that the constraint doesn't really matter at all. All right? You could give 3 times the amount of money to your favorite charity and your profits would only increase by $3. Okay? Like it's small, doesn't matter. In the extreme, if lambda were to equal 0, look what that means. Gradient f equals 0. So that means that the extreme value, while satisfying the constraint, is just the extreme value. You don't even need to say the constraint. It just so happens that the maximum value of f lies on the constraint. So it doesn't even matter. Okay? I just wanted to point that out. Just because we're not interested in lambda doesn't mean nobody is. Okay? Lambda is important in some investigations. All right. So we did this in 2 dimensions with 1 constraint. What we're going to be interested in is doing this in m dimensions, where m is an unknown number with 2 constraints. And that's not going to be easy to visualize. So for that reason, we need another perspective on Lagrange multipliers. All right, and this, as so often is seen, is given to us by algebra. Because algebra doesn't care how many dimensions you're in. Geometry does. All right? So instead of that beautiful diagram, we have algebra. So what we're going to say is, in order to extremize this function subject to this constraint, let's define a new function, f of x, y, semicolon, lambda. Using a semicolon there because lambda is a different kind of variable than x and y. All right? And what we're going to do is we're going to define this function, capital F, as thing we want to extremize plus lambda times thing that equals 0 when constraint is satisfied. Okay? That's what I mean by constraint. Thing that equals 0 when constraint is satisfied. All right? So in our case, we would have that. All right, and the only difference here, well, let's do it real quick. Now what we're going to do is we're going to extremize f in this 3-dimensional space, x, y, lambda. So I'm going to look for critical points. All right, well, how do I look for critical points? I'm going to take derivatives with respect to my 3 parameters. fx, fy, both of these have to be 0, because that's how we critical point. All right? And then what about f lambda? lambda is just hey, the lambda equation is the constraint. So what we're saying is, oh, I want you to satisfy this equation, and oh yeah, by the way, also satisfy the constraint. All right? So it's a real, I don't know, convenient construction for us. All right? Notice also that the point that satisfies these three equations, since it satisfies the constraint, the value of the function at that point is the thing we want to extremize. Because the constraint equation came there. All right? So this does exactly what we want it to do. But it also gives exactly the same thing that the geometric discussion gave. The only difference is that lambda is a different sign. I didn't have to do that, but I just usually write the x and y first and then minus the 10. If I'd written it the other way, then we would get the same sign for lambda and there'd literally be no difference. All right? So that's Lagrange multipliers. We're going to have to use 2 Lagrange multipliers. So we're literally just going to say plus other Lagrange multiplier times thing that equals 0 when other constraint is satisfied. You could add any number of constraints using this approach and do it in any number of dimensions. Okay? So it is a bit more powerful, even though the geometric way has that lovely diagram.